In this video, we're going to introduce the idea of real-time CPU scheduling. Now this will be a little bit different than the stuff we've done before because instead of just saying, oh, processes are done when they're done, right? I mean, I can optimize for how fast they are. I'm going to instead have kind of a hard limit of when something needs to be done. So, okay, what we talked about is basically called, what we've talked about before would be referred to as kind of a soft system, right? Soft real-time system. So if I'm running my operating system, you picture you're on Windows, you're on Mac OS, you don't really have a guarantee of, oh, this process is going to complete in 5 minutes or 10 minutes or anything else, right? It's just, sometimes things get frozen, right? There's not any, kind of thing carved in stone, right, that says it has to complete this soon, right? That's kind of a soft system. It's real time, but soft. What we're talking about here is basically hard real-time systems, right? So this is a true real-time system. What this means is that there was a time bound. So basically, you are guaranteed for this process to complete by this time, right? It's not going to be like, oh, it completes when it completes, right? It could be soon, it could be later. You have a hard bound that says it must be completed by this time. So some example of these, right? Maybe you can think of some of yourself. But I mean, soft real time, right? Stuff we've already seen, right? That's basically a commercial or say user-facing, operating system. A hard real-time system would be something like, a sensor in a car, right? Where it's like, well, I need to pull this every so often, right? And if I don't, pull the sensor, is my vehicle, next to something else or not, well, then there's going to be an issue. I'm going to hit something, right? So I need to have a kind of a hard limit on how long it takes for me to basically to run that process that reads that sensor. So any kind of environment there, right? Or even, you can picture like medical devices. You need to again be monitoring somebody over time. You can't, wait for your process that reads, somebody's, heart rate, right? You don't want that thing to wait, right? You need to basically have that constantly giving you data back, kind of in a bounded amount of time. If you have those in situations, that's when you want to have, a hard real-time system. Now, a hard real-time system, things are a little bit tricky because you get latency from a few places. You get latency basically from the interrupt that's going to be called, right? To basically say, oh, something needs to happen. And then you get latency from basically the dispatch, which is basically spinning up the process that maybe reacts to whatever has happened. Now, some just quick diagrams here, right? You can see it basically have this idea. Let's say, something happens, right? So I need to basically fire off this event, right? And I want this event to occur, right? Maybe it's, every 30 seconds, fire up this process, right? And then the process runs and it, finishes out. How does that look, right? Maybe there's something along the lines of, an interrupt basically gets thrown, right? And then there's kind of this latency that's involved because it's like, well, interrupt goes off. What type is it? Then if I know what type it is, I basically need to figure out, what, process or test thread it belongs to. That'll trigger a context switch, right? So I have, kind of a few things to worry about, right? Eventually I go to, this particular process that's set up to handle that interface, that interrupt, right? And then act on it. There's all sorts of kind of latency time there, right? Between when the interrupt is basically triggered and when it gets to the piece of code that can kind of respond to it. Another kind of broader view here, right, is on the bottom, right? So this is kind of overall the response time, right? So we call this here response interval. It's really just the response time. So response time, if you remember before, is basically how long until we see a result from the process, right? Because the user has to care about that, right? We don't really care about its waiting time so much, right? How long until it's active. What we want to know is how long until it's actually able to do something useful for me. So we care about its response time. And so over here, right, basically have this idea of, oh, my interrupt handling has to occur over here, right? Eventually the process is live, right? And the process generally there's some, well, maybe it needs to grab some resources to do something, right? It could, need something, right? Maybe it conflicts with somebody else, right? Then it finally, runs the code, right? That basically is an answer to the interrupt. And then finally at the end, right, you have, whatever real-time stuff you're running, right? That happens. It basically, there's a whole kind of slew of steps that needs to happen, right? So there's this kind of this pipeline where it's like, I need to do the interrupt handling here, right? And then once I have the process active, it needs to basically deal with getting its resources, picking what to do, and then actually doing it, right? And so I have these kind of these steps where it's like, oh, this is all this time I need to do. And my hope is that kind of I can basically, bound the amount of time that it takes for this thing to run it, right? So I want basically this, right, from, this is time 0 here, right, to this is time n or time t. That should be a certain size, right? So I want that basically that whole thing to complete, in 20 milliseconds. I need that because I want my answer back from my process when I want it, right? So I want it right now. I don't want to have to wait, 100 milliseconds, 200 milliseconds. I want to know that I'll get it within the next 10 milliseconds or wherever it may be. So that's the idea of a hard system. So it's a little bit different than we talked about before. The other systems were soft, right? Basically, we don't really care when they complete, right? As long as they actually do complete. On the next slide, we're going to talk a little bit more about the model of how we represent a system like this. So in this case, we're going to introduce the idea of what is a periodic scheduler. I put periodic priority because somehow periods specify priority. For us, this is going to be basically a model we're going to use to investigate our hard real-time systems. So we're going to define a few things here. First of all, we're going to say we have, every process basically has 3 pieces. It has a burst time called T, a deadline called D, and a period called P, right? So these are the three things that basically make up each of our processes. Now, for a real-time system, the key is this. We need to hit the deadline, right? So I mentioned before there needs to be a bound on how long a process takes to run. That will represent with a deadline. We'll say that there is this deadline, right, that every time the process runs, it's going to take at most this long, right? So that's kind of our difference from before. The other difference, right, is simply a notion of period. And I guess I can go and ask you guys right now, does it seem reasonable to model processes as being periodic, right, as in happening again and again over time, over a regular time interval? Now, for the situation of real time, that does seem reasonable because hard real-time events tend to be something that is kind of sensor related, right? You're needing to pull this thing over time. You need to constantly get back your result. That's very periodic, right? There's not like a lot of times in a hard real-time system where it's like, well, I suddenly have something occur out of the blue that I need to take care of really fast. I mean, certainly that can happen, but majority of the things we have, right, are going to be periodic, right? Things I do over time and I want to get kind of my answer back on a regular basis. So this is a pretty decent model for that. Some other terminology here, we'll basically say that a process's rate is 1 over P, right? So the inverse basically of its period, right? So this is its rate over here. So terminology. Last note here is that basically I have it, so 0 less than T, less than D, less than P. What that's saying is that basically my process burst time, right, is greater than or equal to 0 and less than or equal to my deadline. My deadline is greater than my burst size, greater than or equal to my burst size, and then less than or equal to my process, my period length. My period length is greater than or equal to my deadline, right? So that's kind of how these things are ordered, right? So they're kind of increasing there. And the question there is why. That should not be too bad to figure out if you think about it for 1 second. The reason there, right, is basically that my burst size better be less than my deadline, otherwise I've already lost, right? If my CPU needs more time, my process needs more time than I have in my deadline, clearly I'm not going to hit that deadline, so that'll be broken. Over there to the right, basically it's the same thing, right? My period better be greater than the deadline. Otherwise, my periods basically will overlap, right? So in the same deadline, I'll have multiple things to do, which would also be bad. So I need my deadline basically to be shorter. We already answered that second bullet point there. What type of processes model? Something periodic, right? So something like polling for a sensor. Is this accurate for real time? Yes, right? Just think about medical devices. Think about smart cars. These things are very likely to occur. Over here at the bottom, right, we have the picture, the diagram, how this looks. So I have my periods. Here I have basically 3 periods. And you can see, right, there's this little CPU burst, right, in time t. Then there's a deadline, right? So this is basically the point in time by which you're obligated to be done with this, right? So this would maybe be something like, P0, right? It's the same process running over and over again. That's your deadline. That's when you got to finish, right? And then your period is, how often this thing occurs, right? So notice when the period is over, basically we spawn a new burst, right? So we go again and again. So it happens again over time. And I have, right, basically my 3 different segments here, right, each representing a different period that I have that process running, in a little bit of time. Then, obviously we meet the deadline. Then eventually, right, we go to the next one, run it again and again and again. So the question here on the slide here is basically, does this mean the process will require more time or less time, right, as period increases? Maybe think about that for 1 second. So if you think about that, generally they'll require more. And the reason they require more is because if you they require less, right? As your period becomes larger, you're basically running less frequently, right? And so you can imagine here for increased period, it'd be like, well, I don't really need that extra time, right? I kind of have, all of this here now is kind of being, unused. I don't really worry about that. So that's fine. Now, if I make my period, though, lower, right, if I make it shorter, what happens is I'm basically giving my process more opportunities to run. So it's going to run more often. Well, if it runs more often, it basically has more opportunities to get CPU time, right? So more CPU time, it's probably going to make more use of the CPU. So shorter period, probably more CPU, longer period, probably less. I say probably in both cases because it depends also, how big is this thing, right? But generally, right, lower period means, more frequency of running it, right? So more opportunities to run code means more uses of the CPU.